Hi, welcome to Dr. English's review of chemical bonding part 3, where today we are going to focus on covalent bonding and properties of molecular compounds. So the focus of today is to go over what is a covalent bond, how are covalent bonds formed, using Lewis dot diagrams to represent covalent bonds, and looking at properties of molecular compounds. In the next review, I'm going to go into a little bit more detail about polyatomic ions in covalent bonding, molecular bonding, coordinate covalent bonding, and some just other issues with bonding, chemical bonding, that will sort of wrap up this particular unit. So the first question is, what is a covalent bond? And we'll see the prefix co, which means together, and valent, which really means valence electrons. So covalent bond is all about the bond that is formed between nonmetals sharing valence electrons. That's what we're going to be looking at here. So if we look at this first point, electrons are shared between atoms to complete a full octet. And that's going to be different than ionic bonding. With ionic bonding, we had a full transfer of electrons. With covalent bonding, we are going to be sharing those valence electrons. So in other words, we're not going to be forming ions, at least not in this general definition that we're looking at right now. So we are just sharing valence electrons to get a full octet between nonmetals. And again, typically is going to occur between two nonmetals and can be further classified into polar and nonpolar covalent bonds, which we'll talk about in more detail in a little bit. So if we look at this little animation right here, we have a fluorine atom coming in with another fluorine atom, and this overlap that we see right here is going to be our covalent bond. And we're going to look at that in more detail by representing these bonds in terms of valence electrons through the use of Lewis dot diagrams. So how are covalent bonds formed? Well, covalent bonding is all about valence electrons and achieving our full octet. So let's look at this situation here with two hydrogen atoms, and again revisiting what we already know about hydrogen atoms. So a hydrogen atom has one proton because its atomic number is 1, and again because it's referred to as an atom, protons will equal electrons. Therefore the number of electrons for this hydrogen atom will also be 1. And then we go over to this other hydrogen atom, the same thing, one proton, one electron. So when these two molecules come together, we're going to have this hydrogen atom approach this hydrogen atom, and we're going to have this overlap that we see right here. So this overlap is where we have our covalent bond, because we know the maximum number of electrons in that first shell is 2, because again, if you recall the formula 2n squared, hydrogen resides in that first period, so we're going to have a 1 here, squared 2. So for an electron configuration, we're going to have an electron configuration of 2, because technically hydrogen will have its so-called full octet. So that satisfies hydrogen by looking at that shared pair of electrons right in the middle. So if I was to do the structural diagram of this, I would just say hydrogen and then a dash representing 2 electrons and another hydrogen. So that's how those covalent bonds are forming. It's the sharing of valence electrons. Let's look at another example here. Let's look at hydrogen sulfide, which has a formula of H2S. This is a clear gas. It smells like rotten eggs. It's poisonous, flammable, explosive. Good times. So here we have sulfur with its 6 valence electrons and 2 representations of hydrogen atoms. So again, if we go over the basic information of a hydrogen atom, the number of protons is 1, the number of electrons are 1, because again we're dealing with a hydrogen atom, so the electron configuration for a hydrogen atom is 1. Now, when we look at a sulfur atom, sulfur has an atomic number of 16, therefore it has 16 protons, and again because it's an atom it will have 16 electrons, and its electron configuration is 286. So there we see the 6 valence electrons that we see represented by these black dots up here. 1, 2, 3, 4, 5, 6. Now in covalent bonding, we're trying to get to that full octet. So hydrogen is really trying to get to an electron configuration of 2, and sulfur is really trying to get to an electron configuration of 2, 8, 8 to have the stability of the closest noble gas. So what we'll see here in this animation is this hydrogen atom will come in and will form our covalent bond right here. So now hydrogen has its 2, and sulfur is sharing an electron with the hydrogen, so it's getting closer to getting its full octet. And then we bring in another hydrogen atom, and we get that shared pair of electrons right there. So there's another 2 for the hydrogen, so this hydrogen is satisfied. It has its full octet. And now the sulfur, if we count the number of electrons that are together with the sulfur, we'd say 1, 2, 3, 4, 5, 6, 7, 8, and sulfur now has its full octet and is much more stable, forming the compound hydrogen sulfide. So what does polar mean in covalent bonding? Most of the time when people talk about something being polar, they think about a north pole or a south pole. So in chemical bonding, a polar bond means a bond that is going to have a partial positive pole and a partial negative pole. And when we represent these poles, a lot of times we'll use a lowercase delta symbol. So it looks like a little, almost an incomplete 8. So this means slightly positive or slightly negative. And polarity of molecules, bonds, are really determined by electronegativity values. And you have a list of electronegativity values on table S of your reference table. Now, that being said, a disclaimer here. In a lot of textbooks, they use something known as a Pauling scale, which basically talks about the degree of polarity in a bond. And there's very specific numbers that different textbooks will use, like from 0 to 0.4 and 0.5 to, I don't know, 1 or 1.4. For this particular course, because there is no scale, no specific scale given in the New York State chemistry curriculum, we're going to look at very general trends in terms of bond polarity and determining whether something is a polar bond versus a nonpolar bond. So if your teacher has very specific values that they want you to learn them. But in general, these values will change from website to website and textbook to textbook. So let's look at a polar bond. And an example of a polar bond could be hydrogen chloride. So I'm going to have a hydrogen, a dash, and a chlorine atom coming together, and that represents the 2 valence electrons that's forming this particular bond. Hydrogen has an electronegativity value of 2.2, and chlorine has an electronegativity value of 3.2. So because hydrogen has a lower electronegativity value, we're going to call this hydrogen slightly positive, while the chlorine is going to be slightly negative. And basically what that means is that these electrons that are shared between the hydrogen and the chlorine are pulled closer to the chlorine than they are to the hydrogen, because chlorine has a greater ability to attract electrons to itself. Another example of a bond would be a nonpolar bond. So nonpolar basically means no poles. No poles. So there's not going to be these slightly symbols. One end is not going to be slightly negative or slightly positive. So if we looked at oxygen, diatomic oxygen has a double bond in between it. So 2 shared pairs and 2 lone pairs per atom. Here the electronegativity values for oxygen is 3.4 and 3.4. Therefore, there's equal pull by both oxygen atoms on those shared electrons in between them. So there's no poles between those 2 oxygen atoms. So let's look at specific types of covalent bonding, and let's talk specifically about nonpolar covalent bonds. This is the bond that forms between 2 nonmetal atoms where the valence electrons are shared equally. These are basically the bonds that we're going to see in diatomic molecules, but on rare occasions, there are some situations, like in organic compounds, where a nonpolar bond could be between 2 carbon atoms in an organic compound. So let's look at an example here, the nitrogen molecule. Okay, so we have nitrogen. It has 5 valence electrons. So a nitrogen and a nitrogen. So if it's 5 valence electrons, it needs 3 more electrons to get its full octet. Therefore, it's going to have a triple bond between the 2 nitrogen atoms, each having a lone pair. So again, we see that the electronegativity values would be the same because nitrogen is 3.0 and 3.0. So there's equal pull on those shared electrons between the two nitrogen atoms. Another example that we could look at is ethane. So the carbon in ethane. So ethane has a chemical formula of C2H6. So if we were to draw this out, it'd be a carbon, a line, another carbon, 3 hydrogens. We're going to split that in between the 2 carbons right here. So hydrogen, 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 hydrogen. Now these bonds right here, this bond would be considered polar because it's between 2 different nonmetals and the electronegativity values aren't the same. So we call that polar. But this bond right here between the 2 carbon atoms would be considered nonpolar. Nonpolar because the electronegativity values are the same. Now let's look at polar covalent bonds. So with nonpolar covalent bonds, there was equal sharing between the 2 atoms. With polar covalent bonds, we're going to see that these are bonds that form between 2 different nonmetal atoms where valence electrons are shared unequally. So again, we're going to go to our table S and we're going to look for differences in electronegativity values. So let's look at our first example, and that would be hydrogen bromide. And the formula for hydrogen bromide is HBr, where hydrogen has 1 valence electron, bromine is going to have 7, so it's the hydrogen going to be sharing an electron with the bromine. We'll represent the lone pairs on the bromine right here. Hydrogen has an electronegativity value of 2.2 and bromine has an electronegativity value of 3.0. Therefore, the hydrogen would have the slightly positive charge associated with it and the bromine would have a slightly negative charge. And therefore, the electron density, the shared electrons between the hydrogen and the bromine would be pulled closer towards the bromine. At the same time, let's look at hydrogen cyanide. Now, cyanide is a polyatomic that's listed on your table E, but the formula for hydrogen cyanide is HCN. So if we were to do the structural diagram of this, it'd be hydrogen with a line representing that shared pair. Now, carbon has 4 valence electrons, nitrogen has 5. So they're going to share. This shared pair between the carbon and the hydrogen fulfills one of the valence electrons that the carbon needs. So we're going to put a triple bond between the carbon and the nitrogen, and then the nitrogen has its lone pair. So if I was to go through and assign electronegativity values here, hydrogen would be 2.2, carbon would be 2.6, nitrogen would be 3.0. So if I look at the molecule as a whole, I would say that the hydrogen would have the slightly positive charge because it has the lowest electronegativity value, while the nitrogen would have the slightly negative charge because it has the highest electronegativity value. So therefore, the electron density in general gets pulled closer to the nitrogen than to the hydrogen. So what does polar mean in terms of molecules as a whole? So now we're looking at the entire molecule and not just at the individual bonds. Now, one thing that we have to realize here is that the existence of your lone pair is going to play a role, and we need to understand and embrace polarity arrows. Some teachers use polarity arrows, some teachers don't. I like using them because it gives a very concrete way of looking at a molecule and determining whether it's polar or nonpolar. So molecules can either be classified as having a symmetrical or even distribution of electrons or an asymmetrical and uneven distribution of electrons. So let's look at a type of compound that's a nonpolar molecule with nonpolar bonds. And molecules composed of only nonpolar covalent bonds are going to be nonpolar automatically. So again, we look at these and we think primarily of our diatomic molecules. Nonpolar molecules are automatically going to be symmetrical because there's going to be an even distribution of charge. So an example of a nonpolar molecule with nonpolar bonds could be something like chlorine. So Cl, Cl. That's a nonpolar bond. So therefore, there's equal pull by each of these chlorines on those electrons that they're sharing, so therefore the molecule as a whole is nonpolar. And I like to think of the arrows as canceling each other out. Because they are canceling each other out, therefore pointing in opposite directions, nonpolar molecule. Another example could be diatomic oxygen. So here we have our oxygen, it's two shared pairs, its lone pair of electrons. I'm going to put them at little angles just to change it up a little bit. And again, the electrons that are being shared in the middle here are pulled evenly in two directions. So the bonds here are nonpolar because there's zero difference in electronegativity. Therefore, the molecule as a whole is also nonpolar. And then the final example could be something like diatomic bromine. And remember, bromine as a diatomic is a liquid at room temperature. So again, we have one shared pair, two of the same element, therefore the bond is nonpolar, and each of these bromine atoms is pulling evenly on that shared pair in the middle, so the molecule as a whole is also nonpolar. Notice here there's no slightly positive, slightly negative symbols being used because there's no pull. There's even pull in all directions. So another type of molecule that we're going to look at is something known as a monatomic molecule. And if you look at the word monatomic, the mono part basically means mono or one, and the atomic part means atom. So these are one atom molecules. Most of the time when we think about the monatomic molecules, we think about the noble gases, the group 18 elements. They also have a symmetrical distribution of charge because when you think about them, you know, there's elements like argon. Argon has 8 valence electrons, and if we represent them with Lewis dot diagrams, we just put the 8 dots around the symbol like so, representing an even distribution of charge. Or neon. Neon's the same situation. 1, 2, 3, 4, 5, 6, 7, 8. So again, that even distribution of charge. The only one that sort of violates this is helium, which is also a noble gas, but it only has its 2 valence electrons, but according to the 2n squared situation, that's the maximum number of electrons that that particular shell can hold. Therefore, it's considered having a symmetrical distribution of charge also. Now let's talk about nonpolar molecules with polar bonds. This is always somewhat of a dicey topic for people and hard for them to comprehend. So these are molecules that are going to have polar covalent bonds, but a symmetrical or even electron distribution. And the classic one that we think about here is carbon dioxide. Carbon dioxide, which has a formula of CO2. So when I do this in class, I always start out by doing the Lewis dot diagram of it, then showing the structural diagram of it, talking about the electronegativity differences and how we use our polarity arrows. So if I was to do the Lewis dot diagram of this, I'd start with carbon in the center with 4 dots. 1, 2, 3, 4. And then I'm going to put in my oxygens. So I'm going to put my oxygens on either side because I know that carbon dioxide is linear. So I'm going to say 1, 2, 3, 4, 5, 6. And over here I'm going to say 1, 2, 3, 4, 5, 6. Now, to show the bonding that occurs in carbon dioxide, we need to pay attention to the idea of fulfilling the octet. Carbon has 4 valence electrons. It needs to share with the oxygen in order to get its 8. So I'm going to say that these 2 valence electrons are going to come together to form a bond. These 2 valence electrons are going to come to form a bond. Let's put these 2 together down here, and let's put these 2 together over here. So these are representing bonds. The shared electron pairs, I have them between X's and dots to show the differentiation between the valence electrons that go with the oxygen versus the carbon. So when I do the structural formula of this, I'm just going to have my carbon. Each of those shared pairs is now represented as a line. Put an oxygen over here, another 2 shared pairs, oxygen over here, and then I'm going to have my lone pairs like so. Now when I think about this, I have to talk about electronegativity values because I'm trying to figure out whether the molecule as a whole is polar or nonpolar. Well, carbon has an electronegativity of 2.6 and oxygen has an electronegativity of 3.4 and 3.4. So if I draw in polarity arrows here, going from the less electronegative to the more electronegative, I have one going in that direction and another one going in this direction. And as we see before, if the arrows cancel each other out, either pointing straight outwards away from each other, or in other examples we'll see them pointing in towards each other, basically they're canceling out that pull. So now with the polarity arrows, we see an even distribution of charge. So therefore we'd say this is symmetrical. So when you look at this, there's not going to be a slightly negative or a slightly positive here because this is a nonpolar molecule. Let's look at some other examples. And the first one we're going to look at is methane. So methane. And methane has a formula of CH4. It is an organic compound. So I'm going to start with carbon in the middle, and it has 4 valence electrons, and each hydrogen has 1 valence electron. So we can basically look at this and say, well, carbon's going to have 4 bonds. So I'm going to put it like this. Have a hydrogen here, here, and here. And then I'm going to assign electronegativity values. And I know that hydrogen is 2.2, 2.2, 2.2, and 2.2. And carbon is 2.6. So 2.6. So, yep, 2.6. So if I'm drawing arrows from the less electronegative to the more electronegative, all of these arrows are going to be pointing inwards. So these two arrows are going to cancel each other out. These two arrows are going to be canceling each other out because they're both pointing inwards. So therefore, the molecule as a whole is nonpolar. Now the individual bonds themselves, if we take this from the New York State chemistry way of looking at it, there's a difference in electronegativity, therefore the bond is polar, but the molecule as a whole is nonpolar. Now remember, this is a very simplistic way of determining molecular polarity. In the real world, this is more of a three-dimensional object. We'd call this tetrahedral, but for the sake of talking about polarity of molecules, we can use these arrows to figure out overall molecular polarity. Let's look at another example. Let's look at, make it a little bit more interesting, how about silicon tetrabromide? Okay, so now I have Si in the middle. And like carbon, it's also in group 14, so it has 4 valence electrons. And the bromide represents a bromine, and the tetra, of course the tetra here means 4. So when I do this, I'm going to put a bromine here and have basically that tetrahedral shape again, Br, Br. And I'd have lone pairs all around here. So let's go to the electronegativity values. Silicon has an electronegativity according to table S of 1.9, and bromine has an electronegativity value of 3.0, 3.0, 3.0, and 3.0. Now if you look back over at methane, all the arrows were pointing inwards because carbon is more electronegative than the hydrogen is. In this case though, it's something a little bit different because silicon is less electronegative than the bromine. So in this case, the arrows are going to be pointing outwards. 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 So these two arrows cancel each other out. These two arrows cancel each other out. Therefore, again, the molecule as a whole is nonpolar. The individual bonds, because there's a difference in electronegativity, polar. But the molecule as a whole, nonpolar. All right, now let's talk about polar molecules in general. These are molecules containing polar covalent bonds and have an asymmetrical or uneven electron distribution. Now without a doubt, the one that you absolutely positively 100% need to know how to draw, work with, determine bond polarity, molecular polarity is water. And we know that the formula for water is H2O. Don't call it dihydrogen monoxide. Yes, that is appropriate, but most people in the chemistry world just refer to it as water. So if I was to do the Lewis dot diagram of this, I'd put my oxygen. Oxygen has 6 valence electrons. So there's my 6 valence electrons. And then I'm going to put in my hydrogens, and I'm going to represent those valence electrons with X's. I like to differentiate my dots. I think that's really helpful in determining how the bonds are coming together, to recognize covalent bonds. And then I'm going to circle them. So these are my two covalent bonds. Then I have my two lone pairs right here. So to do the structural formula of this, I'm going to do my oxygen, my hydrogen, another hydrogen down here, and I'm still going to include my lone pairs because my lone pairs are important in determining shape. In a greater scheme of chemistry, like if you go into AP chemistry, those lone pairs are really throwing out these big electron clouds that are pushing these bonds between the oxygen and the hydrogen closer together, which gives us this bent shape that we see right here. Again, if we go through it and we assign electronegativity values, we know that oxygen is going to have an electronegativity of 3.4 and hydrogen is 2.2 and 2.2. So now if we look at polarity arrows with this one, we go from the less electronegative to the more electronegative, like so. So because we have a pole here on a negative end, what we do here is we give that slightly negative sign. So the oxygen is slightly negative, so I'm going to say slightly negative end, and the hydrogen is slightly positive, and this hydrogen is slightly positive. And this is really important on a number of levels. This is going to talk, when we talk about hydrogen bonding, this is going to be important. When we talk about boiling point, melting point, the overall orientation of the water molecule is very important. So again, looking at this water molecule here, the bonds are polar because of the differences in electronegativity, and the molecule as a whole is polar because I have one end that is going to be more negative and other ends that are going to be more positive, and that's where we see these slightly symbols here. Let's look at some more examples of polar molecules. Ammonia is one example, and the formula from ammonia is NH3. And if you forget, that is actually on your reference table under the table that talks about bases, the names of bases. So here's NH3. So I know that nitrogen has 5 valence electrons. It needs 3 more electrons to get its full octet. So just to make things go a little bit faster here, we're going to just throw in the bonds with the hydrogen. I know that the electronegativity values for hydrogen is 2.2, 2.2, 2.2, and nitrogen is 3.0. If I put in my polarity arrows, I'm going to go from the less electronegative to the more electronegative, like so. And again, in a very simplistic way, looking at it from just a two-dimensional perspective, it looks like these two arrows are, oops, forgot nitrogen's lone pair. That's not good. Need nitrogen's lone pair. So looking at this from this perspective, it looks like the two green arrows are canceling each other out, and then we have this other arrow where nothing is canceling it out. And from that perspective, we can say, oh yeah, the molecule as a whole is polar. Actually, again, there's a big electron cloud that is basically pushing these bonds between the nitrogen and the hydrogen down. So we actually get a shape here called pyramidal, because in a three-dimensional aspect, it looks like a pyramid. But overall, if I had to look at the bonds here, I'd say, well, there's a difference in electronegativity, so the bonds are polar. And since the arrows do not cancel each other out, the molecule as a whole is polar. So I'd say that the nitrogen end is slightly negative, and the hydrogen ends are slightly positive, slightly positive, slightly positive, and slightly positive. And again, this is going to be very important when we start to talk about dipole-dipole forces, and more importantly, with ammonia, hydrogen bonding. The other example that we can look at is another organic compound, and that is fluoromethane. So this is CH3F. The meth part comes from the one carbon. The ANE, because, well, there's only one carbon, so it's not going to be bound to any other carbons. And then the fluoro part comes from the attachment of the fluorine atom. So I'm going to start with carbon in the center, and carbon has 4 bonds. Hydrogen's coming off of each one. And then I have my fluorine up here with its 3 lone pairs. We'll do this the right way. And then I'm going to go in and I'm going to assign electronegativity values. So hydrogen is 2.2, 2.2, 2.2. The carbon is 2.6. And the fluorine is the most electronegative element on the periodic table, which is 4.0. So how are my polarity arrows working in this one? Well, for the most part, again, in a very general sense, all the electron density is being pulled up towards the fluorine. So we can sort of think of it like, all right, everything's just sort of going through the carbon, and all of this the general amount of electron density is pulled up towards the fluorine. So in that case, the fluorine would have a slightly negative sign affiliated with it, and then the hydrogens would be slightly positive, slightly positive, slightly positive. So again, most definitely a polar molecule. The bonds are polar because of the difference in electronegativities, especially the one between the fluorine and the carbon, and the molecule as a whole is also polar. Most molecular compounds are going to exist as solids, liquids, or gases. They tend to be soft in nature, they're poor conductors of heat and electricity, and they have low melting and boiling points. And that's just some general properties of molecular compounds. So what did we learn from this very, very long review of chemical bonding? Well, we went over what is a covalent bond. We talked about how covalent bonds are formed. We looked at a number of Lewis dot diagrams that represent covalent bonds, and specifically focusing on polarity of bonds and polarity of molecules. Finally, bringing it all together was the properties of molecular compounds. Need more help? Email me, and I'm always looking for feedback. So if you enjoyed this video, let me know. Hope you have a great day.